Hello and welcome to this video. In this video, we're continuing in the gases unit. This is the second lesson, and we're going to look at the relationship in this lesson between volume and temperature, and again, another formula or relationship, which is called Charles' law. So first of all, getting started, when we had different gases and they were plotted in a graph, showing how as temperature changes, what happens to the volume when the amount of gas and the pressure are constant. They took the graphs and extrapolated to where they took up a volume of 0. They all converged at one point. So let's look at this graph. So if I have different gases, again, I'm manipulating the temperature, so I'm changing the temperature, and I'm looking at how the volume relates. Now the graph between temperature and volume and the relationship between them, again, actually, if I go, did I skip? No, we're good. Okay, sorry. The relationship between them, as I increase the temperature, the volume is going to increase. There is what we call a direct relationship between temperature and volume, because temperature is the kinetic energy of the particles. So when you increase the temperature, you're increasing the kinetic energy. The particles collide and spread apart more. So when temperature goes up, volume goes up. Now, they took different gases, and there are slightly different graphs created, but they're all increasing. This is the data they took. Now, extrapolated means they extended their data beyond what they had to see at what point does it reach a volume of 0. And then no matter which gas and which graph they had, they all converged at this volume of 0 at the same temperature. The temperature is negative 273.15 degrees Celsius. So this is a theoretical temperature. We can nowadays reach this temperature, but back then it was the theoretical temperature that we would reach, negative 273.15, where the volume actually became 0. Now, what does a volume of 0 mean? Remember, volume, as I mentioned in the last video, the volume is the space that the particles are moving around in. So if they're at a volume of 0, this means they are not taking up any space, because remember, an individual gas particle itself does not have a volume. So it means it's not moving, essentially. It's not moving, it's not vibrating, it's not taking up any space at all. This is known as absolute 0. And we actually created a scale of temperature that we will be using in this unit. It's called the Kelvin scale, after the scientist Lord Kelvin, who suggested again that this is the lowest possible temperature you can reach, where particles actually stop moving completely. Absolute 0 of negative 273.15. So what this means is that if we're using, I have some sound effects in these notes apparently, when we're using a small t in our formula, we use degrees Celsius, but a capital T is Kelvin, okay? And in fact, throughout the entire gases units, we will always use a capital T and a temperature in kelvins, okay? So K stands for Kelvin. The relationship is when you have negative 273.15 degrees Celsius, that is known as absolute 0, which is 0 Kelvin. So in order to convert from degrees Celsius to Kelvin, it's actually a little bit easier than doing our pressure conversions. All you need to do is add 273.15, okay? So for example, if you have 0 degrees Celsius, which is our standard temperature, you would add 273.15 and get 273.15 Kelvin. 25 degrees Celsius, which is room temperature, again, add 273.15, we get 298. Sorry about the sound effects if they're getting a little noisy. 298.15. Let me turn my volume down on my screen so they're not so loud. Okay, negative 30. Now make sure you put that in your calculator as a negative. So negative 30 plus 273.15. You will get an answer of 243.15 Kelvin. And then negative 273.15 absolute 0. Obviously, when I add that back, is 0 Kelvin. Okay, so Kelvin is our standard temperature. You always want to, when you're given degrees Celsius, which 90% of the time you're given degrees Celsius, you're going to add 273.15 to convert it into Kelvin. Okay, if you're going from Kelvin back to degrees Celsius, you subtract 273.15. And some questions you might have to do that. But if you're going from degrees Celsius to Kelvin, you add 273.15. So this gets us, like I said, into our relationship and our scientists that studied this relationship. Charles, or Jacques, I can't say French very well, Jacques Charles, and some other scientists as well, looked at the relationship between temperature and volume. As temperature increases, remember I said temperature is a measure of kinetic energy. So if you increase the temperature, the kinetic energy of the molecules also increase. So if the molecules are moving faster, they are colliding with themselves in the walls of the container more often. And as long as the container is expandable, the volume will increase. Okay, that's important. As long as it's not a confined space. If it's a confined space, that means the volume can't change, but the pressure will change instead. But Charles looks at assuming a constant pressure, which means the volume will expand, allowing for the pressure to reestablish equilibrium, getting back to the original pressure you had. Okay, so when temperature goes up, your volume also goes up. And it is a direct relationship. If I triple the pressure, I triple the volume. Okay? However, it has to be the temperature in kelvins that I'm tripling. Then the volume will triple. And we'll look at that a little bit later on. So Charles' law states, oh, this is coming up before the law, there we go. The volume of a gas varies directly with the temperature at a constant pressure and mass. Now what the formula, if you look in your textbooks, what your formula will say is the relationship stands as V1 over T1 equals V2 over T2. Now when we have two fractions like this, it makes it hard to solve for. When I'm rearranging this formula, no matter what variable I'm solving for, my first step would always be to cross multiply, no matter what variable I'm solving for, okay? So what that means is it will be rearranged always in my first step to look like V₁T₂ equals V₂T₁. Since you're not given these formulas, I would just memorize Charles' law in this form, in a linear form, so it's easier to rearrange for, like we did with Boyle's law. So V₁T₂ equals V₂T₁, okay? Temperatures have to be in kelvins, absolutely have to be. If you use degrees Celsius temperature, you will not get the correct answer because it is not, the temperature between Kelvin and degrees Celsius is not changing by the same factor. So what that means is if I have a temperature, let's say in degrees Celsius, and I double it, it'll become 20 degrees Celsius. My Kelvin temperature doesn't double when I make that change though. If I have 10 degrees Celsius, it's starting at 283.15 Kelvin. And when it changes, if the temperature in degrees Celsius doubles, it becomes 20 degrees Celsius, which is only 293.15. So the temperature in kelvins does not double. In order for the volume to double, the temperature in kelvins has to double, okay? So doubling the degrees Celsius does not double the temperature kelvins. So that's why, as I mentioned before, that relationship, that direct relationship has to be with the Kelvin temperature, okay? This is an X, this is not doubling, okay? Volumes, again, standard unit is liters. So this is your formula. V₁T₂ equals V₂T₁. So let's look at some examples of solving this. A balloon was inflated at 27 degrees Celsius with a volume of 4 liters. So that is my T1, except I need to convert it into kelvins. So I need to add 273.15. and this will then be my V1, my volume at that temperature. It says it's being heated, so my T2, again, I add 273.15 kelvins to that. What is my new volume? Okay, so if we start by listing our variables, and I'm going to do that calculation right away. So T1 is 27 plus 273.15. I get 300.15 Kelvin. V1 is in the unit I need it to be in, 4.0 liters. T2 is 57 plus 273.15, which is 330.15 Kelvin. And V2 is what I want to solve for. So we have our formula again, V₁T₂ equals V₂T₁. Now we want to put our variables in and then rearrange, or again, like I mentioned in my previous video, you can rearrange first and then put your variables in. So my V1 is 4.0 liters. My T2 is 330.15 Kelvin. So the V's and T's are on opposite sides. It's not V₁T₁, it's V₁T₂. So make sure you're careful with that. V2 is what I'm solving for, and T1 was 300.15 Kelvin. Okay, so again, I'm isolating for V2. So I'm going to divide both sides by 300.15 Kelvin. Sorry, I forgot the Kelvin in that other side. So they cancel, and I'm left with V2 equals 4 liters times 330.15 Kelvin divided by 300.15 Kelvin. So my Kelvins cancel, and we're left with liters on the top. Okay, remember again, the reason we're dividing by 300.15 is I'm isolating for V2. V2 right now is being multiplied by 300.15. So I have to do the opposite of multiplication, which is division, on both sides of the equal sign. So it cancels completely on this side, and then I'm left with 4 times 330.15 divided by 300.15. And we get an answer for V2 as being 4.399 so on liters. Okay, this is my unrounded answer. It's not my final answer. Sig digs. I do go back and look at the original temperatures in degrees Celsius, how many sig digs they have, and my volume. Everything has 2 sig digs, so I can only have 2 sig digs as well. I'm cutting off a 9, so it's going to round the last digit I'm allowed to keep up, and it will therefore be 4.4 liters as my final rounded answer. Now again, let's check, does this make sense? My temperature went up, so that means my volume should have gone up. It started at 4 and it went up to 4.4. So a good sign that we've done the calculation properly. Okay? So that was example 1. Let's look at another example. A sample of gas occupies a 6.0 liter volume at 110 degrees Celsius. So this can be my V1 and my T1 adding 273.15. What will the final temperature be in degrees Celsius when the volume is decreased to 5.6 liters? So that's V2. We're solving for T2. Now the fact that it wants the answer in degrees Celsius does not mean I leave my initial temperature in degrees Celsius. We cannot do that, okay? We have to convert to kelvins first. We're gonna get our final answer in kelvins, then we will convert it back to degrees Celsius, okay? Because the relationship again only applies to the Kelvin temperature. So if I take 110 and add 273.15, we get 383.15 for our T1. T2 is our unknown, and V2 is 5.6 liters. Okay? So if we write our formula, V₁T₂ equals V₂T₁, My V1 was 6.8 liters. My T2 is unknown. My V2 is 5.6 liters. And my T1 is 383.15 Kelvin. Now I want to solve for T2. So it's multiplied by 6.8 liters. So I have to divide both sides by 6.8 liters. So my 6.8 liters cancels there. And we're left with T2 equals 5.6 times 383.15 divided by 6.8. Okay, my liters cancel and we're left with kelvins. So our temperature is going to first come out in kelvins, 315.53 so on kelvins. Okay, now if the question didn't say it wanted it in degrees Celsius, you could leave it in kelvins and that would be your final answer. But it does say it wants it in degrees Celsius. So to convert from Kelvin back to degrees Celsius, we minus 273.15. Okay, so minus 273.15 gives us an answer of 42.38 so on degrees Celsius for T2. And sig digs, I have 2 digits, 3 digits, 2 digits. We always keep the lowest of everything, which would be 2. I'm not cutting off the decimal, so I don't have to put it in scientific notation. I'm not cutting off a 5 or more, so it doesn't round up. So it would just be 42 degrees Celsius as our final answer for T2. Now again, check if this makes sense. My volume went down, so my temperature should have gone down, which in fact it did. Okay? I think that's the last question. It is. So thank you very much for watching this video of Charles' Law. I hope it was informative.